Hello all, welcome to this session. Hope I am audible. Right?
Good morning, sir.
Yeah, good
Good
morning.
morning, sir.
So today we will revise week 11 and 12. And I hope you guys have already solved mock, which is really important for end term exam. And we have also done one revision session on Tuesday on week 9 and 10. And today we will quickly revise. So as the name suggests, it is revision. So we'll not spend too much time on theory. Right? We'll try to solve problems, but I will also emphasize more on important concepts and that you have to prepare really well for it. Okay, so that's how the session is going to be. We'll start with week 11 and then we'll take a short break and then we will do week 12. Okay. So the very first concept that I'm going to discuss in week 11 is this partial fractions, right? So if I have any rational function of this form, right? So numerator is a polynomial and denominator is a polynomial, and there are the ratio of these two polynomials forms a rational function, and zeros of this function is just the roots of the numerator, and poles are roots of the denominator. So such a rational function, it's need to be written in another form, which is what we call partial fractions, right? So we should know the partial fraction expansion. Okay, so what we have to do, first we have to factorize the denominator. Okay, so if the denominator can be written as a1 minus x into a2 minus x into ak minus x, like if it has some k factors and all these a1, a2, ak's are distinct. So this is case 1, okay? So in this case 1, if all of them are distinct, then we can rewrite the same expression, this whole expression, as sum of k terms. What are those terms? The terms are c1 by a1 minus x plus c2 by a2 minus x plus and so on. There will be k constants c1 to ck such that this f of x, this rational function, can be written as sum of k terms, and each term will have in the denominator only one factor. Right? So if you see, the first term has only a1 minus x, second term will have only a2 minus x, third term will have only ak minus x. Okay, so this can be proven. I think proofs are not necessary right now, but how do we find this c1 to ck's? So that's the main concept now. So how to solve for the coefficients? So one simple thing is you cross multiply this particular denominator on the right hand side, right? So you take this denominator to the right side and multiply with these k terms. What will you get when you multiply? You have a1 minus x that multiplies with the denominator a1 minus x, and this will get cancelled out in the first term, and the other terms will remain as the product, right? So the result will be c1 into product of all the terms except a1 minus x, and this is the first term. Second term this a2 minus x will be cancelled out, rest k minus 1 terms will be there. So I going from 1 to k, except I taking 2, all ai minus x will get multiplied. So there will be k minus 1. What happens to the last term? Last term also, if you see, ak minus x is in the denominator and this ak minus x will get cancelled out. Therefore, the only things that are left is a1 to ak minus 1 in the product. Now, if you carefully observe this, and if I just substitute a1, okay, so if I substitute a1, x is equals to a1, okay, If I substitute x is equals to a1, what happens is, you see a1 minus x will be there in every term except the first term. Right? So if I substitute x is equals to a1, all the terms will go to 0 because there will be a1 minus x in every term. When x takes a1 minus a1 will become 0. So all the terms will go to 0. So the only term that will be left is the first term. First term will be c1 into a2 minus a1, a3 minus a1, a4 minus a1, and so on, ak minus a1. And the left side it will be p0 plus p1 into a1 plus p2 into a2, and so on, pk minus 1 into a1 whole power k minus 1. Right, so from there we can get c1. In general, if I want cj, so for getting c1, I substituted a1. For getting cj, some term cj, j can be anything, 1 to k, anything. So in general, for getting cj, I have to substitute, in place of x, I have to substitute aj, because c2 will not have a2, c3 will not have a3, and so on, ck will not have ak. Like that, cj will not have aj. So if I substitute x is equals to aj, right, so every other term will have aj within it. So all the terms will go to 0 except the jth term. Then the jth term will have this, and left hand side you will have this. For getting cj, simply you have to do this. Okay, so you bring that to the left side, you'll get cj. Either you can do that, or if I just multiply, if you're confused with this, what is all these things? If I just simply take aj minus x in the denominator and the numerator, this whole thing will become f of x, and f of x multiplied by aj minus x, the resulting function, you have to compute its value at x is equals to aj. That's it. Both are same. Both works. Let's do a problem and we will get more clarity on it. Okay, so for suppose, if we are given p of x to be, let's take this only, x minus 1 divided by x square plus 5x plus 6. Okay. So as discussed, first of all, we have to factorize the denominator. If you factorize the denominator, it will become, what will it become? How do you factorize? Anyone?
It
Will
will
this
be x plus 2, x whole into x plus 3.
Yeah, so it will be x plus 2 into x plus 3. So once we have this expression, we said c1, this can be written as c1 by, so these are distinct, right? So 2 and 3 are distinct. So c1 by x plus 2 plus c2 by x plus 3. For getting c1, how do I get c1? c1 basically this p of x, multiply it with x plus 2 and evaluate at x is equals to, this you have to tell. Is it plus 2 or minus 2?
Minus 2.
I hope that is visible. One guy said minus 2. So this is where we get confused, okay, and we go wrong also. So in partial fractions, once you factorize, these are the roots, okay. So a1, a2, ak, all of them are roots of the denominator polynomial, okay. So you have to evaluate at roots of the denominator polynomial. And if you are confused, then write down the roots of the denominator polynomial separately. So x plus 2 into x plus 3 has two roots, right? The roots are x is equals to minus 2, x is equals to minus 3. Okay, so the actual way you should write is x minus minus 2, okay, and x minus minus 3. Alright, so you have to evaluate at x is equals to minus 2. So p of x is x minus 1 divided by x plus 2 into x plus 3 into x plus 2, and you have to evaluate this function at x is equals to minus 2. So here this and this will get cancelled out. We'll have x minus 1 divided by x plus 3. It should be evaluated at minus 2. So if I substitute minus 2, minus 1 divided by minus 2 plus 3, which will result in minus 3 divided by 1, which is minus 3. So C1 will be minus 3. And similarly, we can also compute C2. For C2, you have to take the function p of x, multiply it with whatever the denominator that you have for C2. So the denominator is x plus 3 for C2. So you have to multiply it with x plus 3, and you have to evaluate this function value at x is equals to minus 3, not plus 3. Okay, so again this you do x minus 1 divided by x plus 2 into x plus 3 into x plus 3. This and this will get cancelled out, and you have to evaluate it x is equals to minus 3. And now if I substitute minus 3 minus 1 divided by minus 3 plus 2. So this will be minus 4 divided by minus 1. This will be 4. So this particular rational function can be expressed as sum of two other rational functions, where the sum will be minus 3 by x plus 2 plus 4 by x plus 3. And one good thing you can do is, even though you get the C1, C2, there is always, this is the best practice actually. You can cross verify this by cross multiplying this again and see whether you are getting back p of x or not. So that way you can guarantee your answer, right? So if you just cross multiply and see, the numerator will be minus 3 times x plus 3 plus 4 times x plus 2, right? So it will be minus 3x minus 9 plus 4x plus 8. So if you sum it up, you will see that you will get the numerator to be x minus 1, which is our p of x. So it satisfies. So whatever the values that we got are correct, right? So any other values will not match at all. So this is a unique solution. Okay, so there exists an unique C1, C2, C3 and C case. Okay, so this is case 1, and the case 1 is important. Case 2 you can ignore. Okay, so don't bother about the complex roots, how the expansion and all, you don't really need as of now. The other thing you can focus on if you got time is, what if it is repeated real roots? Okay, So I will not spend too much time on this, but I'll just give you a hint. You just have to follow the same approach. But the only thing is, this 2x plus 1 divided by x plus 1 whole square into x minus 2 will not be only 2. So even though the roots are only 2, okay, the denominator roots are only 2, right? So they are x is equals to minus 1, x is equals to 2, which are repeated twice. This minus 1 is repeated twice, but still the roots are only 2. But that doesn't mean when you do the partial fractions, okay, so I don't think this color is visible. What is this? Okay, so this will not be this. There will be another term in the picture, which is, you can call it as C3 divided by x plus 1. Okay, so now you can work out with C1, C2. You cross multiply and see what terms if I substitute. Right, so you can cross multiply this to the right side, and if you substitute x is equals to minus 1, then some terms will get cancelled out and you can get C1 easily. Right, so you can I will write that also for you. So if I cross multiply, so 2x plus 1 will be x plus 1 whole square into x minus 2 into C1 divided by x plus 1 whole square plus this x plus 1 whole square into x minus 2 into C2 divided by x minus 2 plus x plus 1 whole square into x minus 2 into C3 divided by x plus 1. Okay, so now you can see that this and this will get cancelled out, this and this will get cancelled out, this and this will get cancelled out. The resulting will look like this. So x minus 2 into C1 plus x plus 1 whole square into C2 plus x plus 1 into x minus 2 into C3, and on the left hand side you will have 2x plus 1. So now if you see two terms, so these two terms has x plus 1 in it. So if you substitute x is equals to minus 1, these two terms will go to 0. You can get C1. Similarly, if you substitute x is equals to 2, this and this will go to 0 because both has x minus 2 in it. Right? So substituting, I mean, you should substitute on both sides, okay? And you will get C2. What about C3? How do you get C3? Any thoughts? Okay, first of all, did everybody understood how we can get C1 and C2?
Yes, sir.
Yes, sir.
Huh? So you substitute x is equals to minus 1. If you substitute x is equals to minus 1, on the left hand side you will have 2 into minus 1 plus 1. And on the right hand side, C2 term and C3 term will vanish because it has factor x plus 1. And only term will left is into C1. From this we can get C1 to be minus 2 plus 1 divided by minus 3, which is minus 1 by minus 3, 1 by 3. So C1 we got. If I substitute x is equals to 2 in the above equation, I'll have 2 into 2 plus 1 on the left hand side. And this term will go to 0. This term will also go to 0. And 2 plus 1 whole square into C2. From here, I'll get C2 to be 5 by 9. Right, so 3 square 9. 9 goes to the left side. it becomes 500. Okay, so C1 and C2 are clear. How will I get C3?
Substituting C1 and C2 in that above equation and
Correct.
consolidate it, we'll get
That's
C.
it. That's it. Put some value of X, you'll get C3. Right? So substitute C1 and C2 here. You'll get an equation. Right? So what you'll get? So 2x plus 1 is equals to x minus 2 into 1 by 3 plus x plus 1 into whole square into 5 by 9 plus this x plus 1 into x minus 2 will be x square minus x minus 2 into C3. Right, so now if I expand this is x by 3 minus 2 by 3 plus x plus 1 whole square is x square plus 2x plus 1. If I multiply 5 by 9, it will be 5 by 9 x square plus 10 by 9 x plus 5 by 9 plus C3x square minus C3x minus 2C3. Right, so this is 2x plus 1. So all you have to do is club x square terms together, x terms together and constant terms together and compare the coefficients of left side and the right side. So since left side doesn't have any x square coefficients, so right side should not have x square coefficient. So from there you can see that our C3 should be minus 5 by 9. Right, so just substitute minus 5 by 9 and see whether both the equations are getting satisfied or not. So from there you will see that C3 will be minus. Okay, so this is, so practice some problems related to partial fractions, case 1 and repeated roots, and you will be practiced for enter. Okay, so let's move on and talk about trigonometric functions. So trigonometric functions, I think all the trigonometric functions are important, but among them the sine, tan, cos, you should really focus on the first trigonometric function that we learn. Okay, so sine and cos we have already seen, but go back, see how sine and cos behaves. These things we already know. Tan also is like just the ratio of sine and cos, right? So, and the graph of tan x will be like this. It goes from minus infinite to plus infinite. And if I see in the right triangle, tan theta is basically the opposite side length divided by the adjacent side length, which will be a by b, right? So there are some standard values of tan. Just you should really use to these standard values. It will not be given for you in the exams, right? So either you remember or you know the tricks to remember, or you know the graphs of it, and then from there you get it, or get it somewhere, get used to this. Tan 0 should be 0 because sine 0 is 0. So if you remember the sine and cos plots, that is sufficient. Okay, so there are some standard values. Tan pi by 4 be becoming 1, tan pi by 6 is 1 by root 3, and tan pi by 3 is 1. And if you see in one particular period, maybe from minus pi by 2 to pi by 2, right? So it is an increasing function. So tan is an increasing function in a given interval. Okay, and tan is an odd function, just like how sine behaves, because it is a ratio of odd and even. which eventually becomes an odd function, right? So tan minus theta becomes minus tan theta. And from the graph, you can see it is just, if you just shift your graph by pi units, we will get the same, right? So it is same as saying, even if you shift all your values by pi, so tan x plus pi will give us tan x, the same tan x graph. Okay, so that is the period. We call it as a period. If you guys have studied, then you would understand this. Okay, so that is tan, and secant also is like 1 by cos x, whatever cos x properties you know, then you can also derive this secant x, because it is just 1 by cos x. You can go through this. Some standard values also given to you. Cosecant also is 1 by sin x. It is not really that important, but go through the standard values. Cot is 1 by tan x, right? So the most important things comes here. So you should know the derivatives and integrals of this standard trigonometric functions. So tan x derivative is, even though you don't remember the formula, I suggest these are not difficult formulas to remember. But even though you forgot the formula, tan x, we know it is sin x by cos x. From there, if you know the quotient rule of the derivative, right? So use that, and eventually you will get to secant square x. And secant x derivative is secant x tan x. Cosecant x derivative is minus cos x, cosec x, cot x. So everything you can do it if you know this derivative, right? So no need to by heart the formulas. Okay, so same with integrals also. Yes,
Professor, I
yes.
just noticed that the assignments of week 11 are particularly challenging. So when we solve these derivatives and the integral of hyperbolics and trigonometry, I mean, in the exam, will it be that
No,
difficult?
no.
Okay.
Because we know that you have access to all other AI tools right now, right? So in graded assignments. So you can make use of that, and you can solve the graded assignments. Whereas in exam, it is time bounded, and we do know that if the problems are too difficult, it consumes a lot of time. So it will not be given in that final exams. Final exams you can expect a lot easier than the graded assignment level.
Okay,
Okay.
thank you. It's very comforting. Thank
Yeah,
you.
thanks. All right, so let's continue. So these derivatives and integrals are also important, but again, as I said, if you know the integral, how to do the integrations and standard methods, and if you know how to do the derivatives, all these formulas can be derived. And yeah, so these identities are important, not the left side identities, the right side identities. Why I put this is because of this. Okay, so sometimes the expression might look very big, but using these identities, you can simplify the expression and then work on the simplified expression, not on the bigger expression. Okay, so for that, these identities will help us. And mostly the first identity is very well known to us. Even the second and third should also be very well known to us. If not, then you can sit and try to derive them so that you won't forget it. Okay. Yeah, that's all in trigonometric functions. Now let's come to inverse trigonometric functions. Okay. So inverse trigonometric functions are basically whatever the trigonometric functions just now we studied, right? So the inverses of those trigonometric functions are nothing but the inverse trigonometric functions, right? So sin x inverse is sin inverse of x, right? So cos x will have its inverse as cos inverse of x. Tan x will have its inverse as tan inverse of x. Okay. So sometimes what happens is, even though we are saying it inverse, right? So as we know, the inverses should satisfy this condition, right? So f inverse x, f inverse of f of x should give back me x. Similarly, f of f inverse x should give me x, right? But in trigonometric functions, what happens is, this may not give you x in all the range, throughout the range. Okay, so what we do is we restrict a domain to make it one to one. Okay, so I hope I made a sense here. So trigonometric functions are usually not one to one. Right, so if they are not one to one, inverses won't exist, right? So we have studied this long back. So functions which are one to one only will have an inverse function. So for talking inverses for trigonometric functions, we need to restrict the domain such that the domain that we are restricting makes the function one to one, right? So once it becomes one to one, then the inverse exists, and then we can compute the inverse and plot the inverse also, right? So we'll do that, and these things are really important for in term point of view. Okay, so sin x, we will restrict our domain from minus pi by 2 to pi by 2, not from 0 to pi. Can anyone tell me why? Why we took the domain to be minus pi by 2 to pi by 2? Why not standardly take 0 to pi for all trigonometric functions as the domain? Any answer from anyone? Okay, so if you plot sin x in 0 to pi, you will see sin x to be like this. And is this 1 to 1? Is this function 1 to 1? So we will choose the domain such that it should be 1 to 1. So sin x, when chosen between 0 to pi by 2, sorry, minus pi by 2 to pi by 2, it covers from minus 1. So minus pi by 2, sin minus pi by 2 value is minus 1. So it covers from minus 1 to 1. Right? So it covers all the range values if you restrict your domain to be minus pi by 2 to pi by 2. So therefore, we choose sin x domain to be minus pi by 2 to pi by 2 and range to be minus 1 to 1. So it will cover from minus 1 to 1, even from the plot you can see. Whereas cos x, again, if you choose minus pi by 2 to pi by 2, it will just be again this half semicircle, which will again break the property of 1 to 1. So for cos, what we do is we choose from 0 to pi, so that such that it will cover all values from 1 to minus 1. Right? So these are not the only domains that I have to choose. You can choose any domain, but these are some standard generalized domains. Right? So you can also take pi by 2 to 3 pi by 2 for sin x. So there also sine function will look 1 to 1. Alright, so these are not sacred. Okay, for tan x again we will take between minus pi by 2 to pi by 2 and it will cover the whole range minus infinity to plus infinity. Similarly, you can see for cosec, secant and cot. Okay, so now once we restricted our domain of sin x to pi, minus pi by 2 to pi by 2, and the range to be -1 to 1. Now I can define sine inverse of x, which is now range becomes domain and domain becomes range. So sine inverse of x will become sine inverse of x is a function which takes inputs between -1 to 1 and outputs values between -π/2 to π/2, and the graph looks like this. And some standard values are sine inverse of 0 is 0 because sine 0 is 0. Sine inverse of half is π/6. Sine inverse of 1/√2 is π/4, right? Because sine π/4 is 1/√2, right? So like this. So sine inverse of √3/2 is π/3. Sine inverse of 1 is π/2. Similarly, sine inverse of -1 is -π/2. Right? So sine inverse of minus x is minus sine inverse x because sine inverse of x is also an odd function. Right? You can see the plot, sine inverse x plot. Both this blue and green curves will be symmetric to y is equals to x. Okay. And sometimes what happens is, let's say you are asked to compute sine inverse of sine theta. What do you think this will be? Will this be theta?
Yes, sir. It depends upon the range we are taking.
Correct. So I didn't mention anything about theta. For example, I take theta to be 2 pi. Right. So let's see. So this is sine inverse of sine 2 pi. What is sine 2 pi? 0.
Yes, sir.
So sine inverse of 0 is
0.
see. This is 0. So theta is 2 pi, but the result has come out to be 0, not theta. Right? Something strange, right? And what if I take theta to be, let's say, π/4? This is sine inverse of sine π/4. Sine π/4 is 1/√2. Sine inverse of 1/√2 is
5/4.
π/4, which is theta. So if I take theta to be π/4, it is giving me theta. Let's do one more thing also. So let's take theta to be 3 π/4. Now let's see what we will get. So this is sine inverse of sine of 3 π/4. What is sine 3 π/4? Come on, these
It's
are
1/√2.
very standard. It is
1/√2.
So this is sine inverse of 1/√2. What is sine inverse of 1/√2?
5/4.
Π/4. And this is not theta again. So what is happening? For some theta values, it is giving back me theta. For some theta values, if I take theta to be 0, then I'll get sine inverse of sine 0, which is again 0, which is theta. Alright, so in this case, I got back theta. In this case also, I got back my theta. But in the other two cases, I am not getting theta back. right? So something is really fishy. So what could be the reason? Even though theta can take any value, sine inverse range is fixed. Sine inverse range is between minus pi by 2 to pi by 2 only, right? So if your theta is in between minus pi by 2 to pi by 2, then you will get back your same theta. But whereas your theta goes away from or greater than pi by 2 or less than minus pi by 2, sine of that will give me some value. Whatever the value I get, sine inverse of that, there will be an equivalent value within this interval minus pi by 2 to pi by 2. Right? So what I suggest you guys is, I'm not going to do. I want you guys to try this out. Okay. So try to get the values or plot this function for different thetas or for all theta. Plotting is like almost tells you that plot this, and not only this, you try to plot cos inverse of cos theta. Okay, similarly plot cos of cos inverse theta. So even this also. So what do you think cos of cos inverse theta will be? Any thoughts on that? Will it be simply x? Sorry, will it be simply theta?
No, sir.
Plotting this sine of sine inverse theta also. Okay, so you'll see a strange difference between these two plots and these two plots also. Okay, so try to plot them and see. Okay, so similarly inverse of, there exists inverse of cos. Cos x will have the domain to be 0 to pi and codomain to be minus 1 to 1. For cos inverse x, it will be minus 1 to 1 will be the domain and 0 to pi will be the codomain. And some standard values are cos inverse of 1 is 0, cos inverse of root 3 by 2 is pi by 6, cos inverse of 1 by root 2 is pi by 4, cos inverse of half is pi by 3, cos inverse of 0 is pi by 2. Right? And unlike sine inverse of minus x, cos inverse of minus x is pi minus cos inverse of x. Right? So this is like, this is neither even nor odd case, because from the graph also you can see, you shift this by pi units down and then you will see some sort of oddness, odd kind of behavior. Okay, so cos inverse of minus x will be pi minus cos inverse of x. Alright, so similarly inverse of tan also there will be inverse. It is called tan inverse of x. Tan x will go from minus pi by 2 to pi by 2 to minus infinity to infinity. And tan inverse x will have domain to be the whole real numbers and the codomain to be minus pi by 2 to pi by 2. Okay, and these are the standard values, and again tan inverse x is odd function. So tan inverse of minus x will be minus tan inverse of x. Okay, so that is about inverse trigonometric functions, and yeah, so these derivatives are also really important, right? So sine inverse of x, if I take the derivative, right? So these things I think we have done it in week 11, but the final expressions are really important. So the derivative of sine inverse of x is 1 by square root of 1 minus x square, which implies that if I integrate this 1 by square root 1 minus x square, I will get back right. So the derivative of sine inverse of x is 1 by square root of 1 minus x square, which implies if I take integration on both sides, I'll write it in the other way. So the integral 1 by square root 1 minus x square dx will be sine inverse of x plus some constants. Similarly, the derivative of cos inverse of x, right? So cos inverse of x is just pi by 2 minus sine inverse of x. So this will just be integral. If you see expression like this, then this will just be cos inverse of x plus. Right. Similarly, you can also write down the expressions for tan and cot, tan inverse and cot inverse. So tan inverse will have 1 by 1 plus x square, which means the derivative of tan inverse x is 1 by 1 plus x square, again, which implies that if I ask you for the integral of 1 by 1 plus x square dx, it is tan inverse x plus some constancy. Right. So similarly for cot inverse also, you can see it is minus 1 by 1 plus x square. Okay, so it's not only about knowing the derivatives, you should also know how to use them, right? So in some way you can use them in the integrals also, and the derivatives of cosecant x and secant inverse, cosecant inverse x and secant inverse x also you can do it. And yeah, so this is what I meant. So integration using inverse trigonometric functions. So not only 1 by square root 1 plus x square, instead of 1 I have some a square. Yes.
Professor, you ask us to plot this inverse sine theta,
Yes.
inverse
Yes.
cosine theta. But how can I use these plots? I mean, you got an example of question regarding this?
No. So it is just to make sure that it is not exactly theta for all theta values. So you would be seeing some zigzag lines, right?
So
Yes.
like pyramids,
Sorry.
like a kind of structure of pyramids,
Pyramids.
triangle
So
shape.
you'll see some pyramids, right? So if sine inverse of sine x is x, then it should be like y is equals to x line, right? If you just plot. So it is not y is equals to x line. You just have to be really careful when you take, it depends on the domain. So if I just scroll up a bit. So this sine inverse of sine theta will not be theta always. It will change depending on what theta we take. Right? So
Okay.
that I wanted to convey. And you should be careful of what this theta is. So you should not blindly take theta. That's my point there.
Okay, got it. Thank you.
Yeah. Yeah. Okay. So yeah. So these inverse trigonometric functions can also be used in integrations, and this is really important. This integral 1 by, if you see expressions like integral 1 by square root a square minus x square, then its antiderivative turns out to be sine inverse of x by a plus some constant c, right? And you should be careful that our x square value should be less than a square because it is under the square root. It should be positive, right? And whereas you see expressions like you don't have square root, but you have something like 1 by a square plus x square. Earlier, we don't have techniques how to integrate this, but this inverse trigonometric functions helps us. So this will turn out to be tan inverse of x by a plus c, and this is true for all x. And similarly, the other one also. Okay. So yeah. Yeah, that's it. I think this is the proof for that. I just put it here. So if you want proof, all you have to do is some substitutions, and then you will derive you can get to the expression, right? So this integral 1 by square root a square minus x square dx is actually sine inverse of x by a plus c. Okay, so with that, as I said, uh, these are some. So you can actually skip hyperbolic functions for NTEM exam. Okay, hyperbolic and inverse hyperbolic, because there are too many contents to be revised. So I would like to give you some grace in concepts. So these are some important concepts that you have to go through, or at least prepare or practice problems around these topics, rather than spending too much time on hyperbolic functions. Okay, so we'll take a short 5-minute break now, and we will resume at 12. Sorry, at 11, and we'll start week 12. So these are some concepts that you have to go through in week 11. Okay. All right. So we'll resume in 5 minutes. Okay, hope all of you are back. Before I proceed, is there any doubts in week 11?
No, sir.
No, sir.
Okay, great. Let's go to week 12. And as I mentioned in week 12 lectures also, since week 12 has come very end of the course, and since end term is also very, very near, most of the concepts are important in week 12. But today we are going to revise only those concepts that are really more important for end term. Okay, which are the first order linear ODE and second order homogeneous equations. Right, so second order homogeneous differential equation. So you'll see how to solve these two things. And yes,
Professor, speaking of week 12,
Hmm.
you mentioned that we have this RLC circuit question, right? Non-homogeneous second degree
Hmm.
ODE. Then,
Mhm.
I mean, will this be? I mean, will this be a very complicated like a circuit question in final exam? Because we haven't learned this in ESTC
So
course
far,
yet.
I completely agree with you. So even though the question comes from the circuits, it will not be too complicated circuit. Rather, it will be very easy. Or along with the circuit, we will give you the equation. You don't have to design or get the equation from the circuit. Rather, we will give you the circuit equation, how it is governed.
Okay, thank you.
So yeah. So the main key skill that you have to learn from week 12 is, given a differential equation to you, are you able to solve it or not? So that's the main skill that you have to develop. It's not that given the circuit to you, how do you write the governing differential equation? That's not the main. That is also there, but right now, for examination point of view, that's not the main thing. Okay,
Okay,
so
thank you.
yeah. All right, so let's begin week 12, and also this also will do very quickly, so that will save both of our times. Yeah, so let's start. So as we all know, differential equation is basically an equation involving a function as well as its higher order derivatives and some other functions of x. Right. So for examples like this, f prime of x is equals to 4, or f prime of x plus f of x is equals to 2, or right. So f double prime of x plus 2 f prime of x minus f of x is equals to sine x. So all these are differential equations. Right. So and there are examples. This also we have seen. Falling object. If the object is falling, so then there are some certain forces acts on the object, and from that we can actually write down a differential equation, which when solved, the solution is basically the speed at a particular time. Okay, so v of t is actually the speed, and v prime of t plus k by m into v of t is equals to z. This is the governing equation, right? So if we solve this differential equation, then we can get v of t, right? So this also we have seen, and we have also talked about what if the object is thrown upwards, right? So this is falling object with their resistance, whereas if the object is thrown upwards, then the directions of the forces acts will be different, and we have seen that the final expression will look something like this, right? So we can actually do that. So if the object is thrown upwards, v of t will be acting upwards, but the weight acts downwards. Not only weight, even the air resistance, right? So since the object is moving upwards, the air resistance acts downwards, which is k times K times V of t. Right, so then you can the force acting is MA, A is V prime of t. So M into V prime of t is basically the forces that are acting are mg and kvt. Both are in the opposite direction of the ball moving direction, right? So therefore both of them will be minus mg minus kvt, right? So then if you bring that kvt to the left side, divide the whole equation by m, we'll get v prime of t plus k by m v of t is equals to minus g, right? So this is the governing differential equation for this particular scenario. And once you solve this, the result, the solution is basically v of t, which is the speed at a given time t, right? So this is another scenario. And we have also seen this RC circuit with DC source and given some 5 voltage, constant 5 voltage to the circuit and this resistor, and there is a capacitor, right? And current flows through the circuit, and we have the KVL laws, right? So voltage across the resistor is R into I of t, and across the capacitor, the expression would be V of C is equals to 1 by C into integral I of t, which when derivated on both sides, we will have I of t to be C times Vc prime of t, right? So then if I am interested in current, then I will form the expression to be like this, right? So it will become I prime of t plus 1 by RC I of t is equals to 0, and I of 0 initial current can be something. Whereas if I am interested in voltage across this capacitor, or voltage across resistor, whatever it is. Okay, so how would the expression look? So let's say voltage across the capacitor. So I wanted to see how this voltage across capacitor changes with respect to time. So that means I want Vc of t. I want to find Vc. My solution should be Vc of t. For that, what will be the governing differential equation? So I can use all these three things together, right? So I can substitute this I of t here. I'll get Vr of t to be R into C into Vc prime of t. Right, so now Vr of t is Rc into Vc prime of t. I will take this Vr and substitute in the first equation. I'll get Rc into Vc prime of t plus Vc of t plus 5. Is equals to 5. Right, and if I divide the whole equation by Rc, I'll have Vc prime of t plus 1 by Rc into Vc of t is equals to 5x. That's it. So this is a differential equation. And if you solve this differential equation, the solution is basically not the current. Okay, so the solution is basically this voltage across a capacitor. Okay, so the same circuit, but what I wanted to govern, it depends on what I want to govern. So if I wanted to see the current passing through the circuit, or if I want the voltage across a capacitor. Based on that, we derive the differential equation, and once the derived differential equation is there with us, we'll solve the differential equation, and the resulting solution will give us whatever we want. Okay, and all this first order linear ODEs has this general form, which is f prime of x plus some function into f of x is equals to some q of x, and p of x and q of x will be given to us, and f of x is to be solved. Okay, so in falling object case, we have seen, in RC circuit also we have seen, you can map them, compare them, and you can get this p of x and q of x, right? So this RC circuit, maybe this is not DC source, this is just in general. Okay, it's an AC source, so some voltage source is given to us, and it also changes, so it's an AC current. Okay, so the expression will be like this. Okay, so let's see how to solve them, and I'm skipping this easy cases. So we'll see the constant case, something like, if we have expressions with first order I mean we have only one derivative in the equation, f prime of x plus whatever the function that is getting multiplied to this f of x is a constant, so that becomes p into f of x is equals to q of x. Then what we can do is we multiply e power px. So whatever p you have here, you multiply e power px on both sides. And you will see that the left hand side will just become e power px into f of x derivative. And on the right hand side, you will have e power px into q of x. And you just integrate on both sides. If you integrate on both sides, you will see that derivative of integration is like inverses to each other. Both will get cancelled out, and you'll have e power px into f of x. And on the right hand side, since I'm taking integral, it will just become antiderivative of the right hand side expression plus c, right? And then you divide e power minus e power px on both sides. Ultimately, we'll have expression to be f of x is equals to e power minus px antiderivative of. So the challenge is we have to compute the antiderivative of this e power px into q of x. So you don't have to multiply this e power px or do all these things. Given the first order differential equation to you, identify the p. Once you identify the p, you take this q of x and e power px, compute its antiderivative. Once you have the antiderivative, bring that, substitute in this expression. You will get to the solution. Okay, so simply falling object case, p is k by m, right? So if p is k by m, q is g, q of x is g. So if I compute this e power pt q of t, or e power px into q of x, which will be e power k by m t into g, and I have to find its antiderivative first. Once I have its antiderivative like this, all I have to do is take this antiderivative, substitute it here. If you substitute it, ultimately we'll get this, right? And there is some constant c sitting here, because that has come from the integral constant, and you can actually solve for that constant using the initial conditions. So initial conditions could be starting velocity may be 0. At time t is equals to 0, it can be 0. So using that v of 0 is equals to 0 in this expression, you can get your c. And substitute that c value here, and you will see that your v of t will be mg by k into 1 minus e power minus k by t, kt by m. Okay, and you can also plot this. Plotting is also really important. So once you get the expression, you should be able to plot also, right? So you should be able to plot with respect to time. So when time t is equals to 0, it is 0. You can see at time t is equals to 0, e power 0 will be 1, 1 minus 1 will be 0. So mg by k into 0, 0. At time t is equals to m by k, right? So the first interval. So if you take m by k, it will be 1 minus e power minus 1. So mg by k into 1 minus e power minus 1. So at time m by k, it will take this value. At time 2m by k, it will take this value. Slowly. As t tends to infinite, what happens? As t tends to infinite, this term will go to 0. The maximum velocity that this falling object can reach is mg by k, not more than that, right? So it will not take infinite velocity, right? So there is a maximum. Yes.
Sorry, Professor. This means that in the final exam we will be asked to solve this ODE, or we just plug in values in this the final results equation.
No, solve the ODE only. So you have to solve the ODE. Then you should
But-
also be able to plot the ODE curve or the solution curve.
Okay, got it. Thank you.
Okay. So you should develop your skills in both, not one. You should solve the ODE first. So these steps are important. Once you solve that, after the solution also you should be able to plot it. That is also important. That is why I'm dealing both together.
Oh, okay.
Okay.
Thank you.
Yeah. So that is for falling object. Similarly, for RC circuit with DC source also, we can identify P, identify Q of T, then compute the antiderivative. And once you have the antiderivative, substitute that in the expression, you'll get finally this particular thing with C, some constant C. And the initial condition comes from here. So I of 0 is phi by R, and C will be phi by R. So you substitute you substitute t is equals to 0 and t is equals to 0 in this expression. You will see that C to be I of 0. I of 0 is phi by R, so C is phi by R. You substitute that phi by R, you will get I of t to be this. Okay, so this is for I of t. If the equation is for if you want to govern the current in the circuit, right? So if you want to govern, just like as previously I said, right? If you want to govern voltage across resistor or voltage across capacitor, the expressions would be different, right? So the differential equation would be different, and P and Q of T's could be different, and using them find the antiderivatives, and you can take initially voltage across capacitor, you can take it as 0, and then you can get an expression for voltage across the capacitor and try to plot that also. And similarly with voltage across resistor. Okay. So once you get to the solution, it's always good, or it is suggested to plot it and see how the solution expression is behaving. Okay, so here the expression you see phi by R into e power minus t by RC is a decaying expression. As time goes to infinite, the current passing would become 0. Right? So yeah, so that's about first order. Now coming to the second order linear ODEs, as I said, the second order linear ODEs with constant coefficients will have this general form: a f double prime of x plus b f double prime of f prime of x plus c f of x is equals to q of x, and this a, b, c are some real constants. Okay, and this q of x, if this q of x is 0, then it is homogeneous second order linear ODEs with constant coefficients. If q of x is something constant or some sign, or some sinusoids, then it is not homogeneous. Okay, so homogeneous case is very, very simple. We'll have a second order differential equation with 0 on the right hand side. Okay, so then ABC are real constant, and the solution that we are going to guess is some e power Sx is the solution. So S is some constant, right? So then if f of x is e power Sx, if that is the solution, if I substitute them in the differential equation, it should get satisfied. That then I can say it is a solution, right? So if I do that, I will get this kind of expression, right? So this will never be 0 because it's an exponential function. Therefore, this as square plus bs plus c should be 0. Right? So that is called the characteristic equation. Okay, and this is a quadratic equation, right? So, and we know how to solve these quadratic equations. And the solution to this quadratic equation can be of three cases. One is basically this equation has two distinct real roots, and it can be the same real root, or it can have complex real roots, complex conjugate roots, right? So in three different cases, the solution looks different, and we'll see how the solution looks. And as I suggested, homogeneous case solve more problems related to homogeneous case, and you should know how this characteristic equation characterizes the solution, right? So how the general solution is changed depending on the roots of the characteristic equation. Okay, so if the distinct real roots, say s1 and s2, then the general solution will be of the form f of x is equals to some c1 times e power s1x plus c2 times e power s2x. Correct? So why I'm skipping most of the things is because I think we have just discussed these things in the previous week. So the same things are important basically. Okay, so I'm not doing all the proofs again. And for example, if you see, if we have given you this kind of differential equation with some initial conditions like this, f of 0 is 1 and f prime of 0 is 1, then the very first step you have to do is write down the characteristic equation. Okay. So as I said previously also, in order to write down the characteristic equation, you don't have to take e power s1 or e power s as f of x and then find f prime of x and then find f double prime of x and then substitute and then get the characteristic equation. You don't have to do all those things. All you can do is from the given homogeneous equation, you replace, if you see f double prime of x, you replace it with s square. F prime of x, you replace it with s. F of x with 1. If you do that, you will get the resulting characteristic equation, which is s square minus 6s plus 8 is equals to 0. And all you have to do is to solve the quadratic equation, and we'll get 2 and 4 as the roots. Once we have 2 and 4 as the roots, we know since they are distinct, the general solution will be of the form c1 e power the first root into x plus c2 into e power the second root into x. That's it. For getting c1 and c2, what I have to do, I will use the initial conditions. So f of 0 is equals to c1. If I substitute 0, I'll have c1 times e power 0 plus c2 times e power 0, which is C1 plus C2, which is f of 0, which is 1. So C1 plus C2 is 1. Similarly, for f prime of 0, I'll take the derivative 2C1 into e power 2x plus 4C2 into e power 4x. That will be the derivative, and substitute x is equals to 0 now. So once you substitute x is equals to 0, you'll have f prime of 0 on the left hand side. On the right hand side, you will have 2C1 plus 4C2. And f prime of 0 is 1. So 2C1 plus 4C2 is 1. So now we got two equations with two variables. We know how to solve them. Solve them and get C1 and C2 values. Okay, as simple as that. What if the roots are repeated? What if we have repeated real roots? Then the general solution will be slightly different from the first case. Instead of C1 into e power S1x plus C2 into e power S2x, here it is same S1, S1, right? So therefore, we'll have, I think this I have proved in previous live session. If you want, just go back and see that live session. If it is a repeated real root, then x into e power S1x will also be a solution, right? So if S1 is the only root for our characteristic equation, then x into e power S1x will also be a root. Therefore, the linear combination of these two will be the general solution. So the general solution will be f of x is equals to C1 times e power S1x. So this will be common, plus C2 into x into e power S1x. That's it. Instead of e power S2x, we have x into e power S1x. And again, how to find the C1 and C2? We will be given some initial conditions. Use them, get C1 and C2. So the same second order differential equation with some initial conditions given to us. As I said, just replace f double prime of x with s square, f prime of x with s, f of x with 1. You will get the characteristic equation. Right, so once we get the roots of this characteristic equation, it turns out to be it has only one root repeated twice. Then the general solution should look like this. The same root, e power 3x, and the other one will be x into e power 3x. And the general solution will be linear combination of these two. And now what I have to do? I have to substitute x is equals to 0 and take the derivative and substitute x is equals to 0. And you will get two equations. You solve those two equations for C1 and C2. And once you get the C1 and C2, just substitute them. And that will be the solution, final solution. Okay. If it has complex conjugate roots, right? So if it has complex conjugate roots, something like r plus it and r minus it. Okay. So then the solutions are e power rx into e power it and e power rx into e power minus itx. Right. So then it is just the linear combinations of these things. And the general solution is what is important for us. So we'll have sine and cos coming into the picture. So f of x will be e power rx into c1 cos tx plus c2 sin tx. So this will be the general solution, where r plus it and r minus it are the complex conjugate roots. So r and t comes from there. Okay. So this is the example. So here you can see r is 5 by 2 and t is root 7 by 2. Once you solve that quadratic equation, we'll get roots like this. Once r is 5 by 2 and t is root 7 by 2, the solution will look like this. Now substitute f of x is equals to 0 in that. You will get C1 and take the derivative and substitute x is equals to 0. You will get expressions in C1 and C2. Solve the equations again. You will get C1 and C2, substitute them. Right? So in any case, there are three main steps. Right? So step 1 is basically writing down the characteristic equation. This is common for all three cases. Right? Write down characteristic equation. Once you write down the characteristic equation, the second one is to solve the equation. Solve the characteristic equation. Right. So once you solve the characteristic equation, only then you will fall into the classes. Depending upon the roots that you get, your general solution will change. Right. And finally, you substitute the initial conditions. Right. So these three steps are common in all three cases. The only thing that changes is the general solution, and that depends on the solution for your quadratic equation. Okay. Hope this is clear. Yes. Yes, Lavish.
Sir, in general solution, e to power 5x by 2, please explain.
Sorry.
In general solution, e to power 5 by x, please explain this term.
Oh, this one.
Yes, sir.
That is coming from here, e power rx. Because e power rx cos t and e power rx sin t both are solutions. When you take the linear combination of these two, e power rx is anyway common in both. You pull out. You'll just pull it out. Okay, so that is what written here. And r is basically, if your complex roots are r plus it and r minus it, r is basically the real part of your complex roots. So here the real part is 5 by 2. So that is why it is e power 5 by 2x.
Okay, sir.
Okay.
Okay.
Yeah. Okay. So in the non-homogeneous case also, you can primarily focus on two things. What if they are constants? What if they are sin x or cos x? Okay. So not beyond that. Okay. So something like this. These two examples. So if that is the case, how we will solve is, for non-homogeneous case, what happens is we have to solve for homogeneous case first, and then for the non-homogeneous case, and then combine both to get the complete solution. Okay, so suppose g of x is basically the solution for the non-homogeneous case, and h of x is the solution for the homogeneous case. Then g of x plus h of x is the complete solution of the non-homogeneous differential equation, second order differential equation. Okay, and that g of x is called the particular solution. So you would have seen this in class 11, I guess. So particular solution plus the homogeneous solution will give us the complete solution, kind of thing, right? So here also the same thing. How to get this particular solution? All we have to do is guessing. So if it is constant, we guess that the solution is constant. If it is some linear combination of sine and cos, our guess is also linear combination of sine and cos. Even if q of x is given to be sin x, our guess should be r sin x plus s cos x. Okay, so some linear combination of sine and cos. Okay, so guess we'll guess that as the solution, then compute f prime and f double prime and substitute them in the differential equation, and then simplify it or solve it for the unknown constants. Okay, and this is for particular solution, and add this particular solution to the homogeneous solution to get the complete solution. Okay, so solve some problems related to this also, and you don't have to solve some complicated RLC circuits and stuff, and also you don't need that over damped, under damped conditions, so you can skip those parts for now for exam. Okay, so I'm not saying those are not important, you will again see them in future courses, but right now you can skip that part. So RLC circuit with DC source. All right, so yeah, so with that, I think these are some important concepts from week 11 and 12. So I have mostly given you everything. If you just blindly follow this, at least in week 11 and 12, you will be able to score some 65 to 70, maybe even more than that, 75%. If you just blindly just follow the concept that I dealt and the problem, if you solve some problems, you can get 75% of the marks. But for the remaining 25%, you should spend more time on these concepts. Okay, so not like hyperbolic or nor this RLC circuit with DC or DC or AC, both you can skip. So these concepts you can skip actually, but the other concepts you should really focus more, solve more problems, different variations of problems. Then you can score 100 out of 100 in week 11 and 12. All right. So yeah, with that we'll end our session here. All the very best for your final exam. Yeah, if you have any doubts, you can ask me. Yeah.
Professor,
Hmm.
just last last live session,
Hmm.
another professor just mentioned that the course, the week of the previous weeks, I mean, 6, 7, 8. These weeks will we will have like 30% points out of that. So
Not really, not 30%. I would say you can see at max of one problem maybe. That too can. Okay.
Okay. Thank you very much.
Yeah. But you can solve it. Like if you have done quiz 1, quiz 2 reasonably well, so it will not be from some complicated concept from within some week. Rather, it would be like a general which may connected to week 9 to 12. Like it's like that. So 95% will be from week 9 to 12.
Okay.
Yeah.
Thank you very much, Professor.
Yeah. Okay. Anything else you guys wanted to know? Yeah, major part is from week 9 to 12. So focus on week 9 to 12 mainly. You would have seen that in mock also, right? So mock has only
Yes, sir.
week 9 to 12, right? Right. So you might see one problem which may look like it is coming from week 1 to 8, but it internally would have connected with some week 9 to 12 concepts. Okay. Don't just blindly follow PYQs, okay? PYQs are one good. It helps you in one way where you can get practiced of different types of problems, but don't just completely rely on PYQs. Okay. So there are some surprising questions in the exam. I said surprising, not difficult. Okay. So yeah. Yeah, so they are previous year's questions. All right, guys, then all the very best for your NTEM exam, which is going to come in 2 days. Right, so hope you all do well. And yeah, we'll meet in future courses. Thanks all.
Thank you, sir.
Yeah, bye.
Thank you.
Thank you
sir.
very much, Professor.
Yeah, thanks.